In this video, we're going to discuss VoIP, or Voice over IP. VoIP is a pretty cool topic because whether or not we know it, most of us have used it at one point in time. Or maybe you're sitting at a work desk where your company uses VoIP phones. We can do VoIP over our cell phones, if we make any long distance calls. All of that stuff is going to actually be traversing over Voice over IP. So first things first, let's start with some basics. Voice over IP is basically we're going to convert our analog voice, so how I'm speaking now, into digital packets. Those digital packets get placed on the network and then sent across to a remote destination, being your recipient. So by using VoIP, we can basically turn an internet connection into a way to place free phone calls, if you want to think about it like that. And more companies are switching over to Voice over IP. It saves them money. You do have a little bit of quality of service things to take a look at with that, but it also makes management of those phone numbers and those phones quite a bit easier. So if you think about if you were on campus and you were in one building and you were moved to a different building for your office, they would have to transfer your phone number over there. Well, with Voice over IP, that type of management for those phones is super simple. It's just a mapping of a MAC address of that phone to a phone number that we choose, that we assign. So very cool stuff with that. There's different flavors or how we can connect phones up to a VoIP network, and we'll quick run through those. The first one being an analog telephone adapter, or an ATA. What this device allows you to do is take a normal analog phone, like you might find in a house, connect it into a little device, this ATA, and that'll convert it over to Ethernet for you. So kind of what it looks like here is we plug our phone into one of the RJ11 jacks. The Ethernet connection goes out to our router, and if we had a switch or computers, those types of things. And then the WAN connection coming in, of course, is on that internet or the WAN port. Now this is pretty cool because a lot of routers, and actually coincidentally the first router I ever purchased, had this feature enabled in it. I never really knew what it meant. My router had a T-Mobile stamp on it, 2 phone ports, but I didn't really care. I just wanted it because it was, the right price, had the right ports, did what I needed it to do. But there's a lot of companies like T-Mobile or AT&T or Vonage that actually allow you to subscribe to a voice over IP service, and you can bring that into your house that way. We're going to look at it a little bit differently than that. We're looking at it more from the side of we're containing this in our environment, and we could tie in a call manager elsewhere, but something interesting to take a look at nonetheless. The phones that we're going to be using is going to be just a normal IP phone. They look like a standard telephone, but instead of having an RJ11 jack for the connection, it's just using an RJ45 Ethernet jack. These can also come in wireless flavors, so if you didn't have a jack ran to each desk, you could just have the phone connected up via wireless, and that phone would still be able to access the VoIP service. So you see a few things on here. There's the LAN jack. That's basically where we connect the phone into our company switch. There's a PC port. So a lot of companies will have a wire coming from the switch to the phone, then you plug it in from the phone to your computer, so that way they'll only need to run one phone per desk. If you have a separate handset, that stuff's all using normal RJ11 jack, so it's kind of a mix of things on the back of that. Last step we have is just computer to computer, and this is something we've all done. So if we've ever used Skype or Google Voice or FaceTime, any of those technologies, that's just a computer-to-computer VoIP call. So all you need is your normal computer, internet, speakers, mic, and the rest of it, the rest of the VoIP management, the connection, is all happening in the software. So if we're going to understand VoIP and really see the benefits of using this type of setup, let's talk about how older phone systems worked, and that was all circuit switch data. Phones operated a lot like WANs in the sense of how circuit switching and packet switching actually work. So if we look at this pre-1960s, basically every call we needed to make would have to have one physical wire connected through those switches on the 2 phones. So to put this in perspective, if we're going to make a call from LA to New York, or vice versa going across the country here, there has to be copper wires connecting between the source of the phone call and the recipient of that phone call. So these copper wires were connected via switches, and the switching of that happened either manually or nowadays it's happening electronically. But basically, when you're on that phone call, you would tie up all of that physical equipment for quite some time. That's why those long distance calls were very expensive, You're effectively owning a 3,000-mile stretch of wire, if you want to think about it conceptually that way. And it was just basically a not a very good solution. We've all probably seen pictures like this before of old phone switching operators. So when you'd call the operator up, they would figure out where your call is coming from, where you wanted to be routed to, and actually physically connect you via those cables. And that was really the most simple form of circuit switching there. They'd connect you all the way across the US doing this. Now we've obviously replaced the operators in that sense, and everything is done electronically via a circuit switching appliance that looks something like this. So you can plug in all of your phone cables. It's either electronic or sometimes older ones are a little bit more mechanical in sense, where they can make those patch connections going from the source to destination. So how does a normal phone call work? Basically, we pick up the receiver and listen for a dial tone. That means the circuit is there, it's up, it's free and available. We dial the phone number of the people that we want to talk to. That call gets routed through the switch at the local carrier, so whoever your phone provider is makes the call switch. The pictures we just looked at is basically the piece of equipment we're talking about there. The connection gets made between your telephone and the other party's line, so traversing through different carriers and different switches along the way. The connection is going to open up a circuit. You talk for however long you feel is necessary, hang it up, and then the circuit gets closed, which frees up all of the lines in between you. If you look at how much data circuit switching uses, it's not very scalable, and it's not something that's really ideal for us. On a circuit switched phone call, it's typically transmitted over 64 kilobits per direction. So 64 kilobits outgoing, 64 kilobits incoming, creates a 128 kilobits per second phone call. If you do 120 kilobits divided by 8, that's 16 kilobytes every second that phone call is open, or about a meg every minute that the phone line is open. Really, that's not much data. Like if you had a lot of people in a call center, we're talking a decent amount of data, but not something that's unmanageable, but still not the most efficient way of doing things. Packet switching is really nice because just like in a packet switched data network, in a voice-only network, we just look for packets that actually contain voice or words and transmit those. So if there's long pauses or silence on the phone, those don't get transmitted out. We can also compress that data. We can encode it in different ways. There's a lot of stuff we can do to make this more efficient with a packet switch setup. And VoIP uses packet switching to route these calls. Another cool thing about it is we don't have to have a dedicated line from the source to destination. Multiple phone calls can share the same lines basically going through. So packet switching is a really nice way to do this. So VoIP basically, like I said, since the line isn't always up and occupied, so sending the maximum bandwidth through it, we can have multiple phone calls at the same place, same time, covering the same Ethernet lines. We talked about data compression, those types of things, so let's look at how one of these calls would actually work. If I was using an ATA, so like that little box we looked at before, that allowed me to connect an analog phone into the VoIP setup, I would pick up the receiver on my phone. That's going to signal the ATA. The ATA receives that signal, sends a dial tone, so it's kind of just a comfort noise for us. We know when we hear a dial tone that the circuit's up, the line's ready for us to dial. Basically what it's actually doing though is letting us know that we are connected to the internet. We've got that phone service happening. When we dial the phone number of the party, those tones get transmitted into the ATA for digital data and temporarily stored. So it's like when you pick up a phone and start dialing the numbers, you hear the different tones being played. That's what we're talking about here. After that, the phone number data gets sent from my request over to the VoIP company's call processor. So call processor is something sitting over at the provider of the VoIP service. Really what that's job is to do is just map the phone number into an IP address. Once we have that data in an IP address, we can route it across the internet. So we find that your friend's phone, ATA gets their signal and the phone rings on their end. Once they pick up the phone, just like we saw before, the basically circuit is open if you want to think about it like that. All of our voice data is getting routed over the internet. At this point, it's just normal packets, TCP, UDP, IP packets going across the network. So how does the actual analog to digital conversion work? Because this does matter when we start talking about VoIP. We rely on things called codecs, which basically listen to the audio at set intervals, record that information, and digitize it to a packet format. So if you ever heard of audio sampling, this is what we're talking about here. So there's one particular codec that's typically used with VoIP, and that's the G729A codec, which samples your voice at 8,000 basically samples per second. More complex codecs will sample at 32 and 64K, which results in a little bit higher quality phone call. Within those codecs are basically algorithms that help us figure out, is there silence on the call? Do we need to make packets for this data? Should it be sent across? All that kind of stuff. There's soft switches in the network, which basically takes the phone number, passes it over to an IP address, and from there we can look up the IP address of the endpoint we're trying to reach, route that traffic across. So typical phone numbers follow the E164 format in North America, which is the 10-digit phone number. First three are the area code. Next three are typically the region. So like Madison, South Dakota is 256. So if I see a 605, 256 number, I always know it's coming from Madison. And then whatever the remaining 4 digits are the actual number for that handset or that business or office, whatever it might be. So it's good for normal phone numbers, but we know VoIP, it's voice over IP. We need these to be translated into an IP address. So we take that North American numbering plan, basically what we looked at before with the 10-digit numbers, translate those into IPs. What that tells us is where the network's endpoint is, what phone number is associated with that endpoint, and then the endpoint's current IP address as well. Also within the soft switches is a database of all the users' phones and phone numbers. So this is a mapping of a MAC address and an IP address to a phone number. If the soft switch can't find it, it's going to forward it off to the next soft switch in the network. It keeps going down this line until we can actually find that endpoint. Now, last thing to look at is VoIP is pretty complex in how it works, and there's a lot of different protocols that go into making these phone calls over the internet actually take place. So, the ATAs have to basically have client software working with the codec, converts that analog voice into digital voice, the soft switch maps the calls, and now we need the network portion to make this delivery happen. The most widely used protocol for VoIP is the H323 protocol stack. I'll show you what this looks like here. There's a ton of different stuff going into it. As you can see, it uses a mix of IP, TCP, UDP, and then within there's different protocols and controls as well. So like RTP and all of these different specifications. So it's a really complex protocol, but it does what it does pretty well. More simplified protocols you're going to see, especially if you look at cellular stuff, is SIP, or the Session Initiation Protocol. It's basically just developed explicitly for VoIP. So it's a lot more streamlined, more simple to understand, less moving parts in it. Another one you can look at is the Media Gateway Control Protocol. So this is focusing on endpoint control, gives you a few more features like call waiting, bridging in multiple calls, that type of thing. But either way, these are the three that you'll probably see going throughout this. Last big portion of VoIP is talking about quality of service. So VoIP is a big cost saver for businesses, but the disadvantage is quality. Oftentimes, if you have people talking on the phones and they don't like VoIP, it's because they've had poor quality of service management for their VoIP phones. So we want to avoid things like latency, jitter, and packet loss because those things really hinder conversation. Think about if you're just talking to somebody and there's a half-second delay between what they heard and what they responded with, it's going to make that conversation really difficult. So QoS really comes into play here. There's a lot of different call monitoring or quality monitoring software out there. You'll see that referred to as just QM software. Call monitoring typically relates the quality of the call and something called the mean opinion score. So it's a scale of 1 to 5, where 4.4 is technically your highest value you can get for VoIP. If you think about that, basically anytime I take a voice, run it through a codec, put it on the network, transmit it, do all of that stuff, there's some loss that's going to happen with that. So 4.4 is usually the best you can get, but they say anything above 3.5 or better is a good call. Now, call monitoring happens in 2 different ways. It's either active, it was done before the network was spun up, before the users were handed their phones, or passive, where we're actually watching those phone calls in real time. Last thing I wanted to talk about in this video is VoIP cell phones. So lots of our new phones, if you have an iPhone or an Android phone, can make calls over the 802.11 wireless standard. So when you're connected to a wireless network, your phone can use that network, which has a higher data carrying capacity, to make a really good, really clear, strong signaled phone call. Wi-Fi calling is a really cool deal. It's also smart enough to switch back to something like LTE or CDMA or GSM if your call on your wireless drops. So it's pretty seamless, kind of a cool feature to set up for that. If you had an iPhone, the settings basically just go into the settings, phone, turn on the Wi-Fi calling, and same thing with like Android, it's going to ask you, put in your current address. It's basically so if you have to call 911, there's an address associated with where you're at, so they can send those people to help you out in the right location. But anyways, it's supposed to be a kind of an introductory video to VoIP, get you exposed to some of the topics that we're going to cover and look at some of the things that we're going to do with this cool technology.